Alright, this is potentially going to be another dangerously long video, and I'm going to make sure I keep it under 15 minutes so that I don't get cut off on YouTube. So, I don't have my notes. I'm on the computer again, so bear with me. Page 4, Extreme Value Theorem. F must be continuous in order for us to even consider the extreme value theorem. If F is continuous on a closed interval, if maybe it's continuous everywhere, but as long as it's continuous on some interval, then it has to have an absolute maximum and an absolute minimum at some numbers in that interval. So f of c is the y value that the actual maximum value, and it occurs at c, and f of d is the actual smallest value of the function, the minimum, and it occurs at x equals d. So wait a minute, what about a constant function? There is no max or min, is there? Well, remember in our definitions of max and min, it was less than or equal to and greater than, sorry, I'm having my iPad here, my arm's getting tired, less than or equal to and greater than or equal to. Well, every point on this line is less than or equal to every other point on this line, right? Less than or equal to being the key. And also every point on this line is greater than or equal to every other point on that line. So funnily enough, I just made up a word, yes. Every point on a constant function is the absolute minimum and also the absolute maximum. Draw a continuous function, any continuous function on an interval. Does it have both a max and a min? So take a second, maybe pause me and do that. Continuous function. Just give yourself a starting point and ending point, connect the dots in a continuous function and see if it has a max, both a max and a min. So what are the keys to this theorem? Oops, I scrolled away from the theorem. The function must be continuous, otherwise we can't even think about using the extreme value theorem. Like I said in the beginning, it doesn't have to be continuous everywhere. Oh, check that out. It doesn't have to be continuous everywhere, it's continuous on an interval, and if it is continuous on that interval, then it does have an absolute max and an absolute min. Alright, so let's see. Extreme value theorem is an existence theorem. It tells us that a max or min exists, but not how to find it. So, well, I don't need to say any more on that. What do you notice about the slope of the tangent line at a max or a minimum value? So clearly you're not going to be able to work with a neighbor, but if you take a second and again pause me, draw several graphs in the tangent lines at all the maxes or mins and make a conjecture. Alright, so Fermat's theorem. Fermat told us that maxes and mins occur when the derivative is equal to 0. I'm not going to write the formal theorem. In fact, I don't even think Fermat's theorem is in your textbook. I looked a few days ago for one of these theorems in these early sections of this book, and I'm pretty sure it was Fermat's that's not even in your textbook. Poor Fermat. So, Fermat says that the first derivative must equal 0 in order for there to be a max or a min. Now, it doesn't say, well, I'm probably getting ahead of myself, so let's look. Here we go. Yep. Be careful, the converse of this theorem isn't always true. So what's the converse of that theorem? The converse would be if the derivative is 0, then there is a maximum or a minimum, and that is not true. If you think of the cubic function, y equals x to the third, if I take the derivative of y equals x to the third, so write 3x squared. I hope you guys are writing some stuff down. I can't write because I'm looking at my computer, but I will write when we get to the examples. I mean, I can't write because I'm holding my iPad. Anyways, so y equals x cubed, the derivative y prime is 3x squared, and that is equal to 0 when x equals 0, but draw the cubic function really fast. Is there a max or a min at x equals 0 on the cubic function? No. So Fermat's theorem says maxes and mins occur when the derivative is 0, but just because the derivative is 0 doesn't mean there has to be a max or a min. Where am I? Okay, critical number, huge important concept. I hope I'm not making you guys sick with this. All right. A critical number of a function is a number, some number c, in the domain of f such that Either f prime of c is 0 or f prime does not exist. So oftentimes we're looking at f prime equal to 0 because we don't look at functions that don't exist very often or that have discontinuities very often. So I would highlight f prime of c does not exist because people forget that because we don't use it as often. Okay, so to find an absolute max or min of a continuous function on a closed interval, I want to find the values of f at critical numbers of f in the interval from a to b. So what does that mean? Well, first I need to find critical numbers, which means I need to take the derivative and set it equal to 0. And then I need to take those x values that I get and plug them into f. So let me take a second on that. Critical numbers tells me f prime is 0, right? I set f prime equal to 0, I'm going to solve for x. I'm going to take those x values and plug them into f. The function, not the derivative. Okay, I'm not going to go through these steps because I want to do them as we do an example, like always. We'll probably talk about this part in class. Will you guys make a note to remind me so that, because it's going to come up a bazillion times throughout this chapter, so I wouldn't worry about it if you forget to remind me, but, oh good, okay, we're on the examples. This is the last page, so we should be good. Okay, so let me set this up really fast.